proton plus proton reaction. We are in process of understanding this fundamental nuclear reaction in the universe, right, which is responsible for the evolution of stars and the production of elements. Let me quickly summarize the previous lecture. In the previous lecture, I have given some pictorial information about the burning stages, okay, and then hydrogen burning. As part of that, I have shown you why P plus P should go to proton plus deuteron plus positron plus neutron. Why not helium-2 or lithium-3? Because of the high instability. Okay. So, with those reasons, we have concluded that the fusion of 4 protons into helium-4, whose overall Q value is 26.73 MeV, okay, and the effective is minus 0.53 you have to go into, okay, that I have discussed. So, continuing the calculation for neutrinos, okay, because the average energy of the neutrino is 0.263 MeV for 2 neutrinos, because in addition to 4 helium you have 2 positrons and 2 neutrinos, right. I have calculated the effective energy produced in the fusion of 4 protons into 4 helium, and by taking some realistic values of the luminosity of the sun and mass of the sun, we have seen that sun is a middle aged star, but remember that requires the fact that the burning is taking place at the center of the sun, where about 10% of hydrogen is there, and we have done some calculations in the previous lecture. Let us see some more features of this proton plus proton reaction, okay, and then also the burning of deuterium and the burning of helium, if time permits, okay. But mainly we will see the burning of deuterium, burning of hydrogen, and then burning of deuterium, and then burning of helium-3, because deuterium and helium-3 are produced in this P plus P reaction, okay. Fine. So, when I say here hydrogen helium burning, here I am talking about the mass number 3, fine. Please remember, initial reaction is P plus P, it is deuterium plus proton plus neutrino, and then this deuterium is interacting with another proton through electromagnetic force, which gives 3 helium plus gamma ray, and helium-3 produced in another reaction, okay. Helium-3 produced in another reaction reacts with helium-3 produced in this reaction to produce helium-4 plus 2 proton, right. So, this is basically PP chain, and this is basically PP1 chain. There we have PP2 and PP3 also, that I will discuss in the next lecture, maybe if time is not possible. All right. So, as I said, now it is a time to understand the dependence of temperature on the reaction rate when P plus P are involved, P and proton involved. Earlier, if you remember, while discussing the non-resonant reactions, I have shown you that energy produced in this non-resonant reaction is proportional to the reaction rate, and this is proportional to T to the power of minus 2 by 3 and e to the power of minus tau, where tau is 3 E naught by kT, okay, and numerically one can say that this is the formula for tau. So, this is the formula we know, where the reaction rate is related to the temperature, all right. So, if we try to see the dependence of energy on the temperature, we can draw like this, quite interesting diagram. So, this is the energy produced and this is the temperature, starting from say 1 to 100 and say 1 and logarithm scale 10 to the power of 5, 10 to the power of 10, 10 to the power of 15 like this, and 10 to the power of 25. So, one can say that the proton plus proton, the energy produced in this proton plus proton reaction when temperature is changing from 1 to 100 T6 changes like this, whereas if you see the another reaction set which is responsible for the production of helium-4, that is CNO cycle, whose details I will discuss very soon. You can see that up to T6 is equal to 20, it is the proton plus proton reaction which is playing important role for the energy production. Okay. So, that at T6 is equal to 20, the change is taking place, okay, from PP chain to CNO. PP chain involves 4 protons overall, okay, and we can say that PP is main source, PP is main source for sun and stars with mass less than or equal to mass of the sun mainly. And in HR diagram, if you remember, the temperature of main sequence stars increase with mass, alright. So, based on this we can say that the temperature increases with total mass, that is quite natural to understand. That means more massive stars consume fuel more rapidly. The mass is more, the fuel consumption is happening with better rate, that leads to high energy production. However, this kind of stars will have shorter lifetimes. So, this should highlight the relation between temperature, okay, and fuel consumption rate, energy production and lifetime. 4 quantities are involved here. In this statement, 4 quantities are there. Number 1, temperature, number 2, mass, and number 3, fuel consumption rate, number 4, energy production, actually 5 quantities, right, energy production and lifetime. Alright. So, how these 5 quantities are related to each other, we can understand from this dependence of reaction rate on the energy production, and keeping in mind the value of masses from the HR diagram or mass luminosity relation. So, that is the reason initially I have spent some time on the relation between mass, luminosity, temperature and spectral color in terms of HR diagram. So, understanding of HR diagram plays, it is very important to know different features of nuclear burning stages. Alright. Okay, let us continue. Once proton plus proton, the first reaction in PP chain is giving rise to deuterium plus positron plus neutrino, okay, whose Q value is 1.44 MeV, including the annihilation energy. Now, it is time to understand the deuterium. Deuterium is produced, it has to be destroyed, right. The production of deuterium is because of this reaction. What about the destruction? Let me show you some reactions which are important for the destruction of the deuterium. Alright. So, the reaction and corresponding Q value, let me inform you here. The reaction which is well known as part of PP chain, that is whatever deuterium is produced will interact with another proton to give rise to produce helium-3 and gamma ray. The Q value is about 5.5 MeV. What does it mean, my dear? If you measure this reaction proton and deuterium, then you can detect gamma rays. The gamma rays energy will be 5.5 MeV around it, okay. And then the deuterium can also be destroyed by reacting with deuterium produced in another P plus P reaction. So, then this deuterium can be destroyed by this reaction where helium-4 is produced, Q value is this, and the reaction between deuterium and deuterium can also lead to proton and tritium. The deuterium can also be destroyed with the same reaction of D plus D producing helium-3, but giving rise to neutron. This is also possible. Another possibility is when P plus D is giving rise to helium-3, that helium-3 can react with deuterium. Overall whatever deuterium is present, they can undergo reaction with either proton or deuterium or helium-3. These are the available nuclides which gives rise to alpha particle and proton. So, these are some of the possible reactions for destruction of the deuterium. Production is because of P plus P, that is clear to us, right. Another reaction which is possible is deuterium by reacting with helium-3, it does not give you alpha particle plus proton, but it may give lithium-5 and gamma. All these are, remember, exothermic reactions. Okay? And one more reaction, deuterium can also interact with the alpha particle helium-4, which is outcome of a fusion of 4 protons and to give rise to lithium-6 and proton. This is also exothermic reaction. Okay? So, remember, in all these, which is more probable? The question is which is more possible, more probable. See, in this, because protons are abundant when compared to other nucleides, naturally we can say that the predominant reaction is P plus D only, because when compared to proton, no other element is more abundant. So, now it is time to understand the time rate of change of deuterium. Okay? So, it means production rate minus destruction rate. Production rate is, reaction rate is R P plus P, destruction rate, this I should write as R into PD. Okay? So, this should be in subscription. So, this is the production rate and this is the destruction rate via proton plus deuterium. Production rate is because of proton plus proton. Now, this one can write in terms of atoms as hydrogen square, because its identicalness is there, and this is the expression for total reaction rate in terms of reaction rate per particle pair, and you know the relation between reaction rate per particle pair and a total reaction rate in terms of number density. Please write down for both proton plus proton and also proton plus deuterium. Alright. Now, this represents a self-regulating system and which reaches a state of quasi-equilibrium kind of thing, which means that d by dt is equal to 0. See, the capital D and small d, they are not very much different, only thing is that from nucleus to atom state I have represented. Now, from this one can say d by dt is equal to 0, this expression gives rise to this expression. The ratio of deuterium and hydrogen at equilibrium depends on the reaction rates where 2 is in the denominator. Okay? Now, let us see some more features of this D by H ratio. See, P plus P reaction is not via electromagnetic or nuclear interaction, it is via weak force, whereas P plus D is because of EM force. Why I am discussing this reaction? Because it is the reaction which is responsible for the production of deuterium and this is responsible for the destruction of the deuterium. And we are trying to understand the overall mechanism of the deuterium production and destruction. And considering the strength of these two forces, naturally weak force when you take the production, okay, it is very less. So, the D by H is much less than 1. Why? In this you see, this is a weak force and this is the electromagnetic force which is stronger. So, the ratio will be less than 1 only, right? That is what I have written here, and it is of the order of 10 to the power of minus 18. Okay, it is much less than 1. If you take in terms of reaction rate, the ratio of is 10 to the power of minus 18, say at T6 is equal to 5. Now, the interesting feature is that observed D by H ratio is 10 to the power of minus 5. Okay. If you measure the reaction rates individually for proton plus proton, of course, which is not possible to measure experimentally, theoretical one, and then P plus D reaction rate can be measured, there is no problem, because it is via electromagnetic interaction. It was about 10 to the power of minus 18. Whereas, observed D by H ratio, if you take the abundance, it is 10 to the power of minus 5. Why so huge difference? This is one of the interesting puzzles in nuclear astrophysics on which work is going on. Okay? So, one has to look into the production of a deuterium prior to the formation of stars. We have to go before the formation of stars stage, so that whether deuterium is available at that time. Otherwise, observed deuterium, why it is so high? Alright. Now, let us see what is the lifetime of this proton plus proton reaction. As we discussed earlier, it is the about 10 to the power of 10 years. Please understand the symbol of this, this symbol, lifetime of hydrogen while reacting with another hydrogen. it is about 10 to the power of 10 years, whereas lifetime of deuterium while reacting with hydrogen. Why not others? Because we have seen hydrogen is abundant, so other reactions are not very important. It is just 1.6 seconds. See, 10 to the power of 10, 18 years and 1.6 seconds. This is just nothing. This highlights the importance of relative magnitudes of the interaction mechanisms. P plus P is proceeding through weak interaction, and P plus D, which is reason for the destruction of deuterium, is proceeding through electromagnetic, and lifetimes are 10 to the power of 10 years and 1.6 seconds. So, the relative magnitude of strengths involved shows this, reflects the difference in this lifetimes. Now, once helium-3 is produced in P plus D, it can react with deuterium to emit either gamma or a proton. Okay? Now, after this deuterium, I am discussing about the helium-3. All right. Now, this deuterium, if it reacts with helium-3, earlier I have discussed deuterium with proton. Now, if it interacts with the helium-3, then it comes out that the lifetime is about 10 to the power of 4 seconds. Now, please listen to me carefully. Though the reaction rate between helium-3 and deuterium is 7 orders of magnitude larger than this PD reaction. PD reaction lifetime is 1.6 seconds and helium-3D reaction is 10 to the power of 4 seconds. So, about 7 orders of magnitude larger. However, lifetime as expected it is not much lower, whereas it is 4 orders of magnitude longer. I repeat, when deuterium is undergoing destruction via different mechanisms, we have concluded that let us take the only one reaction, that is deuterium is undergoing destruction by reacting with proton, and we have seen its lifetime is 1.6 seconds. Just for the sake of convenience, I am taking another reaction. Deuterium is reacting with helium-3, its lifetime is 10 to the power of 4 seconds. Okay? However, reaction rate is 7 orders of magnitude larger. Okay? The lifetime is 4 orders of magnitude longer. Okay? 10 to the power of 4. So, due to this extremely small density of helium-3, we can see that the lifetime is 4 orders of magnitude longer, though reaction rate is 7 orders of magnitude longer than the PD reaction. I hope you are trying to, you are able to understand what I am trying to say. Because of the extremely low availability of helium-3, lifetime is much longer. Okay? And that is the reason it is insignificant in the destruction of deuterium, Okay. So, because in this previous reaction, the dominant reaction is P plus D, which is giving rise to helium-3, and this helium-3 is reacting with another helium-3 to produce 4 helium plus 2 proton, completing the chain. The time has come to understand the mechanism of destruction of helium-3. With that, we can complete the PP1 chain. All right, let us see. So, the helium-3 burning and completion of PP1 chain. So, when I say burning of helium-3, how it is produced? Please remember P plus D giving rise to helium-3. This is the production rate. Okay, this is the production mechanism. Now, once helium-3 is produced, in how many ways it can be destroyed? It can undergo destruction by reacting with another deuterium and giving rise to lithium-5 or helium-4, or this helium-3 can react with helium-3 again to produce either beryllium-6 or helium-4, or because in 4 protons fusion, helium-4 is the end product. That end product of helium-4 can react with helium-3. With that, helium-3 can undergo destruction, giving rise to beryllium-7 and gamma. Remember, all these are exothermic reactions. Now, the question is, which reaction is important and why? Remember, one has to see the extrapolated astrophysical S factor values, and that shows that helium-3 plus D has large value, and also helium-3 plus helium-3 producing these 2 protons 1, which is the last reaction in the PP1 chain. These 2 seems to be key reactions. However, abundance of deuterium is much less compared to helium-3. See, directly we are not saying that okay, helium-3 is produced. So, to produce helium-4 it can react with another helium-3. But why only that reaction? Why not other reactions? For that, those reactions have to be measured. One has to see the S factor values and extrapolate to 0. That gives us an idea which reaction is important and why it is important. Now, because the abundance of deuterium is much less than the abundance of helium-3, we can say that the second key reaction, that is helium-3 plus helium-3, is the predominant one in the destruction of helium-3 nucleus. Okay? So, this is responsible for the destruction of helium-3. Now, you can always ask, why can't proton, which is highly abundant? Now, I am saying because deuterium is less abundant when compared to helium-3, the original topic, that is destruction of helium-3, should happen through reaction with helium-3 only. But what about protons? Anyway, they are highly abundant. So, helium-3 should undergo destruction by reacting with proton. What is the problem? So, this is where it is interesting thing. Look at here. See, okay, because highly abundant proton can react with helium-3, it will give lithium-4, but it is highly unstable. Okay, it undergoes positron decay and it can give rise to helium-4. No problem, because helium-4 can be produced by this process also. However, the Q value of this reaction is negative, minus 2.5 MeV, and lithium-4 is not particle stable. It is full of nuclear reactions. Initially I told you, nuclear astrophysics, to understand the features of astrophysics and astronomy, the role of nuclear physics comes into picture in terms of nuclear reactions. And as we are discussing the different burning stages, what are the various types of nuclear reactions coming into picture? So, that is where you need to be clear which reaction is exothermic and endothermic, what reaction is possible to lead to the production of which kind of element. So, this whole story, it has to be clear to you. So, go step by step and try to see which reaction is possible and why, and which another reaction is not possible and why. So, this is how you can develop interest in terms of understanding this course with the help of nuclear reactions. I hope it is clear to you when I say that proton plus helium-3 giving rise to lithium-4 is not possible, though at the end we are able to see helium-4. Alright, it is basically endothermic reaction, my dear, right, and lithium-4 is non-particle stable. So, that is the reason proton cannot react with helium-3 and complete the reaction to produce helium-4. So, overall we are in the framework of helium-4 production from the fusion of 4 protons overall. Okay. Now, let us see the time rate of change of helium-3, production rate minus destruction rate. Okay, production rate is P plus P because, and this is earlier I have written this equation. Okay. So, let me correct here. So, it is basically rate of production is R P D minus R helium-3 right. So, this is the production rate minus destruction rate to understand the time rate of change of helium-3. Alright. So, P D, proton atomic number 1, deuterium, I mean mass number I am talking about, mass number is 2. So, instead of P and D and helium-3, I am using the mass numbers in the subscript. Please be careful this transition from symbols to numbers. Okay. So, here the atomic density, number density of hydrogen and deuterium when reaction rate per particle pair is involved, and you know why 2 in the numerator, why 2 in the denominator. See, 2 helium-3 nuclei are involved. Okay. That is why in the production of helium-4, 2 helium-3 nuclei are involved, that is the reason I am using 2, and because the identicalness I am using 2 in the denominator. Okay. I hope it is clear to you why 2 in the is there in the numerator and 2 is there in the denominator. Now, we know that earlier we have established the D by H ratio, reaction rate between proton and proton in the numerator, reaction rate between proton and deuterium in the denominator. See, here I am transforming the equation of this d by dt of helium-3 in terms of d by h, okay, and I am converting finally in terms of only hydrogen and helium-3, no deuterium here. Okay. So, d by dt of helium-3 using this equation one can come up with this expression, alright. Now, as I discussed earlier while talking about the time rate of change of deuterium, this equation represents a self-regulating system, okay, which reaches a state of quasi-equilibrium, that is d by dt of helium-3 is 0. So, if this is equated to 0, then this is equal to this, that gives rise to the ratio of helium-3 and hydrogen at equilibrium, and this is basically decided by the reaction rate of P and P and the reaction rate of helium-3 and helium-3. Alright. Now, let me show you one interesting diagram by considering the mass fraction of hydrogen helium as 0.5 and the density as 100 grams per centimeter cube. I am showing you the variation of lifetimes at equilibrium versus temperature. Please understand, this is a lifetime of the proton against proton, lifetime of helium-3 against deuterium, this is the lifetime of helium-3 against helium-3, and this is the lifetime of helium-3 against helium-4. Similarly, you can see the decay lifetimes when boron 8 is undergoing decay and beryllium 7 which is undergoing decay. That is the reason it is almost a straight line, the lifetime, right. And what is the lifetime of beryllium 7 when it undergoes destruction with proton? So, we have considered lifetimes, different lifetimes of different kinds of reactions at different temperatures, Now, the point which is of our interest from this diagram is the lifetime of helium-3 against the destruction of helium-3 is about 10 to the power of 5 years, whereas the lifetime of deuterium against proton, earlier I have shown you, it is 1.6 seconds. 1.6 seconds. What does it mean? There is no role of deuterium induced reactions in burning of helium-3. Okay? So, though initially I have said deuterium abundance is less when compared to helium-3, it is the helium-3 plus helium-3 which is predominant role, which is playing predominant role in the destruction of helium-3. In terms of lifetime, we can understand that the lifetime of helium-3 against helium-3 is 10 to the power of 5 years, whereas against deuterium is about just 1.6 seconds. So, in the destruction of helium-3, there is no role of deuterium. So, what all these things tries to convey us? In the production and destruction of a specific nucleus, what are the nucleides which are playing important role and why they are playing important role? So, this is what I am trying to explain you by showing the reaction rate equations, okay, for deuterium and for the helium-3. So, I hope it is clear to you from this diagram. Okay. Now, another question which is of our interest is, what is the total energy produced via P plus P reaction? Remember, the energy production via P plus P reaction depends on whether helium-3 equilibrium is reached or not, because it is the helium-3 plus helium-3 which is giving rise to 4 helium plus 2 protons, right. And it was clear that overall rate was controlled by, it is always controlled by the P plus P reaction only because of its weak interaction and slow consumption. Now, please remember, instead of going to 4 protons, I am stopping with only the fusion of 3 protons. Fusion of 3 protons giving rise to helium-3, isn't it? How? 2 protons giving rise to deuterium plus positron plus neutrino. So, 2 protons are over. Another proton reacting with deuterium giving rise to helium-3, right. So, overall 3 protons when they undergo fusion to give rise to helium-3, the Q value involved is 6.936 MeV. Please remember, it is 0.263 MeV neutrinos on average, earlier I have shown you, right. The loss of neutrinos energy is 0.263. So, overall the effective energy is 6.673 MeV, 6.673 MeV. So, with this one can understand the energy produced in the stars via P plus P reaction. How? See, the energy is when 3 protons are giving 3 helium, okay, this is 6.673 total reaction rate of P plus P, MeV centimeter cube, okay, and per second. So, this is the energy produced in the reaction when the total reaction is controlled by the P plus P reaction only. Either you can write R11 or PP, that is up to you. Whereas, for 3 helium reaction, okay, in the next step, when overall 4 protons are involved, energy released is 12.860 MeV in this reaction, right. So, the energy production is when 3 helium plus 3 helium is happening, it is basically 12.86, the reaction between helium-3 and helium-3. So, MeV centimeter minus per centimeter cube and per second. Okay. So, with in the reaction model calculations, normally there are several steps which I am ignoring here. So, it is sufficient to understand that at equilibrium, when d by dt of 3 helium is 0, we can show that 2R33 is equal to R11, which gives rise to, already this we have discussed in the previous slide, the energy produced is 13.103 R11 MeV centimeter per cube, per centimeter cube and per second. Okay. So, to summarize today's lecture, I have discussed more salient features of P plus P reaction. In particular, when P and P produces a deuterium, in how many ways deuterium is undergoing destruction and what is the predominant way of destruction, and with that how to understand the lifetimes of the destruction mechanisms. And when P plus D is giving rise to helium-3, in how many ways helium-3 is undergoing destruction, and finally, the rate of production and the rate of destruction of helium-3 has given some information about the reaction rates and the ratio of helium-3 quantity and hydrogen quantity. Finally, the energy produced via this P plus P reaction, which we are calling as fundamental nuclear reaction, it is about 13 MeV multiplied by R11. So, overall the reaction rate is decided by the proton plus proton reaction, and the overall reaction rate for proton plus proton reaction multiply with 13 gives you energy produced because of this particular reaction. Okay. So, in the next class, I will discuss some more types of PP chains. Okay. See you soon. Thank you so much for your attention. See you.